This is an IIPMT 2000 question in electric charges and fields, and a very interesting question. It says a charged wire is bent in the form of a semicircular arc of radius A. If the charge per unit length is given for us as lambda, what is the electric field at the center is? Let us draw a diagram first to understand that what he has given for you. It is given that the charge is, a wire is bent like a semicircular wire. So, it is not exactly semicircular. So, I will draw it again, semicircular wire bent in the form of an arc whose radius is equal to A, and hence this is also equal to A. If the charge per unit length is given for you, charge per unit length is given to us as lambda, what is the electric field at the center? That is what he want to calculate. So, now the charge is distributed throughout the wire, there will be electric field strength due to each part of the wire, and we have to add all of them. So, what do we do now is, we will try to calculate electric field intensity due to a small portion of the wire whose length is equal to dl, who is making an angle d theta at the center, right. So, you can say let small portion length is dl. That implies I can write charge on that small portion can be written like charge per unit length multiplied by length. Charge per unit length is given as lambda, multiplied by length is dl, where what I can write that dl as, because dl is not a part of any of the given data, dl is a small angle, very definition is arc by radius, arc of that is dl, by radius of that is nothing but a. That implies dl can be written like a d theta. That implies small charge on dl, dq can be written like lambda into dl means lambda into a into d theta. This small portion has a charge dq. Due to this dq, if I keep a unit positive charge at the center, as dq is also positive, that positive charge applies a repulsion on the unit positive charge kept at the origin, that is called electric field intensity dE, right. So, we can say this is how the dE is acting, but if you see carefully, this is making some angle with the x axis theta. So, this angle also becomes theta. This dE now can be resolved into components. Adjacent to theta is dE cos theta, opposite to d theta is dE sin theta. But what we can understand is, there is component like this everywhere between this point and this point 0 to pi. So, I have to find electric field due to a small component, and then I have to integrate so that I will get the entire picture. Let us do that, right. So, that implies dE Ex, dE Ex can be written like 1 by 4 pi epsilon naught dq into 1 by a square, that is E, and I have to write the cos component because you are writing dEx along the x direction. Now, in the place of dq, as I have told you, I can write lambda a d theta by a square cos theta. I have already found dq, I am just substituting that value. 1 a can be cancelled. So, this value is 1 by 4 pi epsilon naught lambda by a cos theta, that is small dEx. That is what I mean by dEx is the small component of electric field generated due to this small element. that is only a small component, right. So, to get total electric field along x axis, I shall integrate integral of dEx equal to integral of this value lambda by 4 pi epsilon naught a cos theta, where that component could vary anywhere in between here to here 0 to pi. Now, let us simplify this to get an answer. Integral of differentiation of dEx is Ex equal to lambda by 4 pi epsilon naught a is constant, integral of cos theta is sin theta, whose limits are from 0 to pi. I have applied this integral of cos theta and wait, I have missed a d theta here, this d theta. So, this d theta will be there, this d theta also will be there. So, integral of cos theta d theta can be written like this value, integral of cos theta is sin theta. So, if you simplify this, lambda by 4 pi epsilon naught a, upper limit has to be applied first in the place of theta minus lower limit, that is lambda by 4 pi epsilon naught a, sin 180 is 0 minus sin 0 equal to 0. So, 0 into everything equal to 0. So, what we understood is all electric field components together cancel for each one, and hence the resultant electric field becomes 0. That is about x axis. Similarly, we can find out, like I have written dEx, I can write dEy here. So, dEy here is the same thing. When you write y, I will get a sine component 1 by 4 pi epsilon naught dq by a square sin theta. So, I can do the same, I can just continue writing the same steps. What is the difference is, instead of cos theta, I will get a sin theta. How do I get that? 1 by 4 pi epsilon naught dq is the small charge, that is lambda a d theta by a square, and sin theta 1 a will cancel. So, lambda by 4 pi epsilon naught a sin theta d theta is dEy. Integrate that, integral of dEy equal to integral of lambda by 4 pi epsilon naught a sin theta d theta, where the limits are again 0 to pi, so that he can complete the entire semicircle arc. Integral of differentiation of ay is ay lambda by 4 pi epsilon naught a, differentiation integral of sin theta is minus cos theta, whose limits are from 0 to pi. So, this minus can be written outside, minus lambda by 4 pi epsilon naught a cos pi minus cos 0, that is minus lambda by 4 pi epsilon naught a into cos 180 is minus 1 minus cos 0 is also 1, minus of minus becomes plus, that is 2 lambda by 4 pi epsilon naught a, 1 2 will cancel. So, our answer is lambda by 2 pi epsilon naught a, that is the answer for the problem. So, this is actually a concept, a derivation in regular syllabus. So, you need to do this derivation to get to the answer, right. While doing this derivation, you can learn that how do you calculate the electric field when the charge is distributed over the surfaces. The same approach can be done for the other kind of the shapes and bodies too. That is it, and thank you for watching.